yet. Please just, my stream is ready to go. Okay, looks like we have started already. So, or not? Yes. Okay, so hello everyone, and welcome to everybody who is new. We are streaming from Colombo, Sri Lanka, and this week we will have New Year holidays. That's why we decided that there will be no lectures this week. So we already had lecture number 1 and 2 last week, and you can find the recording on YouTube. So today we will have Q&A session on the topic on lecture 1, and tomorrow similar question and answers session for lecture number 2, and then we'll continue with the third lectures next Monday. So, okay, welcome. Okay. So let me open my slides. Right. So we continue our course on verification of smart contracts on the Ethereum blockchain platform. And our first lecture was on formal verification of software. And here I'll just briefly answer all the questions I got during this time. First, second, we'll go through the theory test I suggested you just maybe for self-assessment and for those who are interested in getting certificate from Exactpro. And third, we will speak about our practical task. Again, I suggested you as a homework. So let's proceed. So first, we'll start with questions related to my lecture. And again, probably the most difficult, the most simple question is related to motivation. Why do we really need to know all this mathematics about proofs and axioms, etc.? And let me just remind you of this analogy from my lecture. It's like about this engine on the picture. Surely you don't have to know what's inside if you're just driving car, but again, it's a definitely fascinating topic, and especially if you consider not just drive a car, but maybe design a new car or update, just suggest new updates, new version, new idea, new tools, then definitely it will be helpful for you to know what's inside, what's under the hood. So that was probably the first question. Why do we need this mathematics? So the mathematics is not necessary, but it could be useful, especially if you're interested in just the development of this tool. Okay, second question I got was about this table. Let me just remind you the context. So I compare testing of system with formal verification of system. And then line by line, I suggest you some pros and contras. Like testing is simple and straightforward, and even if you just have small amount of money, you can invest it into testing and get some information about the system quality and improve it, etc. For formal verification, it's not the case. Usually, it's much more expensive and requires more time and resource. So you probably will need to allocate some people and expect maybe a couple of months before you get some real result. The second line is about knowledge and accessibility, then about applicability, etc. So the question I got was about the last line. So I claim that testing is not really well reusable, while formal verification is perfectly reusable. Let me just explain what I mean. So for formal verification is the basic idea. It's very similar to how science evolves. So you start with some domain, then you analyze this domain, then you produce some model, some theory, some maybe axioms and some theorems about this domain. And once you prove the theorems, they can be used forever. In that sense, formal verification is highly reusable. So once you establish some property of particular algorithm, some results, some properties, etc., then you can be sure that these properties will be true forever until you have the same model of the system. Now regarding testing. So usually okay, according to my testing experience, you almost never start with just a system which is created from the scratch. So you have this kind of life cycle for a system which evolves from one version to another, and definitely some results of testing of the previous version could be reused. First of all, there are bug reports. So once you have a clear and well-organized database of bug reports, even if system is completely rebuilt, re-implemented, and all this refactoring is done, and maybe it's even written in a different programming language using different frameworks. Anyway, usually bugs are kind of could be almost the same. So by just applying, trying to check the previous bugs, it's always helpful. It's called regression testing or similar way. So surely all these bug reports are usable. Second, test cases surely are usable. So once you analyze the system and you created some nice ideas for test generation, for test selection with really nice coverage, then definitely all these results could be used for another version of the system. Okay, take into account that this version may have some additional functionality, but the part you have already kind of analyzed and tested, it could be reused, or you can use the same test cases. So test cases definitely are usable, and the same is regarding domain knowledge. So even if you have just completely different system, but again, for example, it's related to some self-driving cars, or maybe some stock exchange, something else, all the knowledge you got about the domain, some specifics, some specificity, some special cases, some specific requirements, some maybe hidden assumptions, etc. So definitely all these are useful, but not the testing results. So when I'm speaking about usability of testing, I had in mind the testing results. So assume you have like version 2.3 of your system, and you executed all your tests, and you finally came with the result that like the system is like 85% okay, like it like 85% of your tests are passed, the other 15% are failed. Then you get another version of your system. You cannot rely on this information at all, because it may happen that some scenario was successful, now it is not. It may happen then some scenario was failed, but now it's kind of fixed. So the information about the system run, about the result of the testing is not really reusable. That was the idea of this last line. But for verification, it's slightly different. Okay, you still okay to answer more questions, and I'll try to so please write in the chat, and I'll try to answer today or maybe tomorrow or next time. So that was about this slide. Okay, let's go next. Right, the next question I got, it was during the lecture. What about proof of termination? So let me remind of this slide. It describes the Hoare triple, which says that you have a kind of precondition, psi in this case. Then you have kind of a program, and in this example, this is while loop. And then you have postcondition, and this triple formalizes the following statement: that when the precondition is met, executing the command establish the postconditions, and here we kind of we implicitly assume that the program terminates, because if it doesn't terminate, then it doesn't make sense to speak about condition. You will never get to this final state. So everywhere here in the Hoare logic, we assume that system terminates, and then prove that once this assumption held before the computing, then we can be sure that this and that those will be true after the computing. So the reasonable question was what to do if we are not sure whether the system terminates, and the typical way to prove it is shown on this slide. So usually you need to figure out some parameter, in this way it's written P, which is decreasing each time you call your statement in the loop. Like for example, and then this property you can easily formulate in terms of this Hoare triple. So we assume as a precondition that P equals A, and it doesn't matter which A here is a free parameter. And then we try to prove that after this statement is performed, then the parameter will be less than A. Surely we assume that A is integer or something, a discrete parameter. So once we have this proven, established as a theorem, we always can be sure that while B is full, and that it always terminates at least, or sorry, at most in P steps, but surely it could be more fast. And definitely we assume that P, okay, there are some natural restrictions on P and A, but in general, this is the way to prove the system termination. And again, sometimes for some loops, to find such P is quite straightforward because in quite many cases you have this explicit loop counter, which is decreasing each time a loop is executed. Sometimes it's more tricky to figure out this P, and it's not necessarily, could be maybe not integer, but maybe some vector of integers which behaves in certain way. But anyway, this is generally the approach to prove the termination of your code. Okay, I assume this is clear or not, more or less. Okay, so thank you. Yes, so this must be decreasing integer parameter in simple case, and in more sophisticated cases, it could be something more specific, but anyway, it must be discrete and well-founded. Okay, another question I got was related to different theorem provers, and this table is copied from Wikipedia just to show you that there is kind of a huge world of different theorem provers. And here I mentioned just 4 parameters. The first is whether this prover uses higher order logic or not. You see some do, some don't. The other parameter, whether they support dependent types, and probably the simplest example of dependent types probably is vector or stack, right? You can have, in some cases, you can define just a stack type, which depends on the particular type of elements, and then immediately you get stack of integers, stack of real, stack of something. But for some other systems, you will need explicitly to do it each time because dependent times are not supported. Then some systems do support proof automation, other more or less focused mostly on manual proofs. And again, you see some yes or no, but definitely most of them are in green area, so proof automation is supported. And another nice and very important feature, especially for applications in computer science, is once you proved correctness of an algorithm, can you generate the code of the algorithm automatically? And some of the system do support this feature. So once you prove that this algorithm terminates and this Hoare triple is valid, you can just push one button, and after some time you just have immediately formally verified code of this algorithm. For some it's not, and there are just 4 parameters, and definitely there are more. And again, you see the column number 3 that different systems are written in different languages. Then notice this column number 2 that different academic and commercial companies are involved in creating their own systems. You see at least 2 from Microsoft. You see Cornell and Stanford, PBS is from Stanford, American universities. You see Koch from French university. You see it's over the world, some people in industry, in academic environment in Europe, in America, and different places, they are working on creating automated theorem proofs. So there's just a whole big area which is active for, I assume, maybe at least 30 years at least. So I believe that PVS was already on the market when I was a university student, so it was quite a long time ago. The same with COG and Uprel and other systems. So you see there is a huge field, and I suggest you to dive in if you find it interesting. And one comment which probably one of you will find interesting, that this is a field that many people believe will be kind of next generation of artificial intelligence. But if you try to think about what artificial intelligence is the idea that computer will behave like a human, right? So, and usually we try to think that computer as a small kid who's just born, and everything related to machine learning. I mean, all these neural networks and different topics. They try to solve tasks which usually like 3, 5, 7 years old kids are able to solve, like to distinguish cat from a dog or something else. But then when a child becomes older and enters school, he or she has mathematics class and tries to learn formal reasoning and logic. And this is kind of next generation of intelligence. And this is exactly what automated theorem provers are about. So, and many people expect that after this hype of machine learning and artificial neural networks, there will be another hype for automated provers and automated reasoning, just to teach the computers real logic. Okay, so our course touched another hot topic, not only blockchain, but also AI sometimes. Okay, let's go ahead. Yes, another question was related to our work with this prover. And some people notice that sometimes we say, okay, let's prove some universal property, like the equations I had on my lecture, like commutativity, etc. And when we switch to practical examples, we usually trying to build a model. And from first glance, it may look like two different approaches. So either you prove something or you find a model for something. But this simple fact from the logic shows that this is actually the same. So instead of proving that for all x some property p holds, one can prove that there is no exist counterexample. So there is no exist x such that not px holds. And in mathematics, this is a very well-known approach that in order to find proofs, you just show that counterexample doesn't exist. And this is called proof by contradiction. And this is kind of this is well-known approach. I assume many of you probably know this idea, and it is widely used in formal proofs too. So yes, that were the questions related to my slides. Let's now go to the theory test and see the questions. Okay, the forum is still online, so if you don't like spoilers, just switch off now and try to do it yourself. But in general, the questions are more or less simple. Let's see. So, is it possible to? Okay, let me make it bigger. It's probably better, right? So the first question was: is it possible to guarantee 100% on correctness of a system using testing? And everyone who is at least had some experience with testing definitely knows that the answer is no. But in theory, we can imagine a very simple system which has like two states and one transition between them. So I would suggest that the correct answer is this: no, unless the system is really very finite. Okay. So the second question: what is axiom? Okay, let's see the options. An idea that it proposed for the sake of argument, so that it can be tested to see if it might be true. So the idea, so surely not. Axiom is not something that we kind of expect might be true. So I would say that this is not the correct option. So let's switch to the other one. Define a clear expression of something in speech or writing. Again, this is not the correct option because it says nothing about whether it's true or not. And from axiom, we expect that it has to be like evident and simple. Information drawn from personal testimony, a document, a material object used to establish fact. This is not about statement, it's more about witness. And then a statement or proposition which is regarded as being established. This is definitely the correct answer. So axiom is a statement or proposition which is regarded as being established. Okay, proof. I see some already my previous attempts to answer. So what is a proof? Okay, a short piece of writing on particular subject. Surely not every writing is a proof. Logical steps that take you from your hypothesis to the conclusion. Looks like a correct one. A detailed investigation and analysis of a subject. Definitely, okay, that sounds close, but not yet, because investigation is not really a proof. So you may find a lot of information, but that doesn't take you from axiom to conclusion. Exchange on the verge of, this is more definition of more like definition of discussion. So the correct answer here is clearly this one. So proof is a logical steps. Proof is logical sequence of logical steps that take you from your hypothesis, from axiom to the conclusion. Again, theorem. A statement or assertion that expresses judgment. Okay, this is not theorem, it's your opinion probably. Something that is known to happen or exist. This is more about fact, but not theorem. So usually theorem needs to be proved. A general proposition not self-evident but proved. Yes, this is the definition. Not self-evident but proved by a chain of reasoning. A confident and forceful statement of fact or belief. No. Okay, postcondition. A condition that should be always true in an object life. Definitely no, because the object life could be quite complicated, and we expect postcondition to be correct at the end of the computation. So this is more like invariant, but not postcondition. A condition or predicate that must always be true just after the execution. Yes, sounds like correct. A condition that must be true for your method to code to work. This looks like maybe precondition, right? So before you call function, you need to check some condition. So it's before, not after. So it's precondition. A data type that can go and type check, not precondition. Okay, so correct answer here is definitely this one. So postcondition is a condition or predicate that must always be true just after the execution of some section of code. Okay, now the task. Is the following Hoare triple correct? So before, you see the statement is very simple. We just assign a plus 1 to x. And before execution, we know that a is greater than 1. And we need to check whether it's really correct that always after this statement, assuming the precondition holds, you'll have that x is greater than 2. Okay, so a is greater than 1, then a plus 1 is greater than 2, right? And a plus 1 is exactly what x. So maybe one of you will need some maybe piece of paper and pencil, but I assume this is definitely correct. And for every y, a and x. Okay, formal verification establishes the correctness of algorithms with respect to formal specification. Sounds okay. That the systems may meet expectations of the stakeholders. Definitely no, because stakeholders could be very different and most of requirements could be not related to functionality, but verification is always about functional requirements. So second is not correct. Absence of bugs in the system. Unfortunately, no, because again, so not all bugs are functional bugs, and even more, formal application works only with formal specification. So if something just somehow implicitly known but not formally specified, then it may happen that this condition is not met, and no one can guarantee you absence of bugs if the specification is not formalized. So no, again. So the last one, that software can be used by consumers to achieve quantified objectives with effectiveness, efficiently, and satisfaction. Okay, that looks like a dream, right? That software can be used by consumers to achieve quantified objectives. Okay, this is definitely a dream, but again, formal application can guarantee any satisfaction, and again, can guarantee any efficiency. So, right. So here, the first answer is the correct one. Okay, and another question. What is the meaning of the statement in the tree syntax? Oh, this is just fun. So you see this parentheses, this is just one parameter. This is second parameter. And the main property here is the greater than relation. So this is greater than, and this is implication. So this one is definitely wrong. Okay, let's see the first, the left part. The first part is multiplication. X is the first parameter of multiplication, and plus something is the second. So let's see, multiplication, it's here. So we have x times x plus 2, plus x2 is greater than, and the right part is multiplication, and then here we have addition, x1, x. So definitely it's number 4. Okay, and then the last question of our test. What happens when the tree is asked to prove a statement which is not always correct? Okay, a runtime exception. It terminates with counterexample. It runs into infinite loop. The system crash. Okay, since I assume developers smart guys. This is just, even I try to put myself into the shoes of the one who never used the tree. But if you design a system which has to kind of automatically prove something, definitely you will make it like not correction, right? If something is wrong, and even runtime exception is not. So it's the 2 or 3. But okay, in this case, we assume that it's number 2. Yes, by default, it finds counterexample, and this is exactly how we use it in testing. So we try to prove something, and then if you fail, then we immediately get a test case, which is exactly as a counterexample. Yes, so we are done with the theory test. Okay, I hope you find it fun. Okay, let's go ahead. Okay, so the last part for today's seminar is to see our practical task in the tree. But let me remind you the slide from the lecture. So basically, input of the tree consists of 3 parts. We declare variables, then define our constraints, and then just call some function whether you need to check satisfiability, get model, etc. And the task was to check if the following holds. I mean, this is implication, some linear arithmetic here, some simple restriction there. So, okay, as a mathematician, this is my first education was mathematics. I did the first step manually. So let's prove it by contradiction. So what's mean that implication is not correct? Implication is false if the premise is correct. So this and this holds, while the conclusion is false, right? So to find counterexample, we need to find integer values x and y such that this holds and this holds. This provides us that premise is correct. And then you see I replace here greater than with less than or equal. So we need to be sure that this is false, sorry, and this is false. So basically this transformation is more or less straightforward, and definitely Z3 can do it itself as many as other automated theorem provers. But okay, I can't resist just to do it manually because that's how it works. So you see, we start with this kind of more or less complicated, I mean, not complicated, but statements complicated structure. So basically it could be quite simple and easy, but in real industrial application, the definition of such property can take like 100 pages, like different if, then, else, and combinations and or negation, implication, whatever. So that's exactly the best case for applying the tree or other theorem prover. And then the system transforms it into some collection of this kind of systems, and then we'll need to write this into the syntax of the tree. So again, we declare here two variables, x and y, and then just basically go one by one. We assert that this one is greater than 3, this sum is greater than 2, y is less or equal than minus 3, and this x is less or equal than minus 3. Okay, let's go to online version of the tree. Okay, notice you see here, let me make it larger. Yes, this is it starts as example we had. Let me just, oops, can't I copy it? I can't copy it from PDF. Because it's in the full screen mode, right? Yes. Okay. Okay, let's copy here, paste here. Okay. Let me do this from the other screen. So yes. So you see, I pasted into the. Okay, so let's make some mistake. For example, what if I forget press here and just ask to execute it, and then we see output. Okay, it doesn't crash. It says me that line 9, 1, 2, 3, 4, 5. It's okay. So you see, it works quite fast and well. And okay, let's see the result. Execute now. Okay, model is not available. So I should probably remove this one, get model. So we check satisfiability. It's not satisfiable, then it doesn't make sense to ask about the model. So let's run again, execute, and unset. So you see the result is, so this combination is unsatisfiable. So we prove by contradiction. That means that indeed the initial implication is correct. Okay, and now what will happen if you see it says that y is greater than minus 3. Let's slightly weaken it. For example, let's replace okay, how to switch to correct window. No. Did I close it? Okay. Let's, how did it disappear? Okay, let's try again. So I go here. Ah, yes, it's here. So, for example, let's display -3 with 3, for example. Then it's slightly weaker condition. Let's execute it. And you see, now it's satisfiable. That means that we can ask for a model. So because in real life, you're not just interested whether it's correct or not, but if it's not correct, if there is some model, then you'd like to see the actual values of x and y. So I'll return here this, paste back this get model statement and execute. And you see, it says that the counterexample is y equals 0 and x y equals 3. So y is 0, y is 0, and x 3. Okay, so then probably yes. So that's how it works. And just maybe last remark. So I have written it in as a 4 separate statements, just to be as close to the initial system as could be. But in general, surely you can write it, for example, this way, just because 2 statements is just a conjunction. So if you write and, it should go this one. So you have this and this. Okay, let's see. So one more parenthesis. Okay. No. Line 4. Okay. Line 4, column 34. Open. Because it's not that human readable syntax. So this is the end of this one, and this one. Make one more. Okay, let's see. Insert command number 4. Okay, there is some mistake, but don't know why. Oh, definitely need another one. But okay, it's not that important. So if you like the idea, just play with it, and this is basically how it works. So any questions, comments? Let's return back to our slides. So right. So we started with this implication. I manually converted into the system of inequation, but actually I could do just a simple conversion from this initial form into the tree. Then you call this check satisfiability and get model system. You can do it either online or you can install it on your system. And definitely, there is not only one interface. You can also call the tree from Python, for example, and create this system and the call automatically from your script. And that's how actually the tree is mostly used. So surely it's not feasible to write down manually all this input. Usually it's created automatically by some script or library function. That's it. So we conclude for today. I see you tomorrow. Tomorrow we have questions and answers session for the lecture 2, which is related to blockchain technology and Solidity code. Okay.